Hi everyone, welcome to another episode of the Bio-Inorganic Chemistry lecture. Today we are going to see the dioxygen management proteins. In that, specifically we will concentrate on myoglobin. First, let's see what is myoglobin. We know that myoglobin is a small globular monomeric protein which consists of a single polypeptide chain bound to the heme molecule. We know what is heme molecule. It is the prosthetic group which is present in hemoglobin and myoglobin. It is having a porphyrin ring system which is having iron 2 plus in the center.
Or we can say it is the non-protein part of myoglobin.
It functions as an intracellular oxygen storage site in cardiac and skeletal muscles fibers of vertebrates. So, what is the function of myoglobin? It functions as an intracellular oxygen storage site. So, that is the function of myoglobin. It is the main oxygen storage site in vertebrates. It also helps in regulation of cellular oxygen in the repairing tissues. It transports oxygen to mitochondria for oxidative phosphorylation. Now, let us see the structure of myoglobin. It is a monomeric protein. It is having a molecular weight of 17 kilodaltons. The protein chain of myoglobin contains about 153 amino acid residues and it is folded about a single heme group. Here you can see the porphyrin ring system present in hemoglobin and myoglobin. You can see iron is present in Fe2 plus state and it is being bonded to 4 nitrogen atoms of the pyrrole ring system.
The 4 pyrrole rings have 4 methyl, 2 vinyl and 2 propionic acid side chains.
So, this is the heme group and surrounding this heme group there is the polypeptide chain. The 5th ligand of iron is provided by the imidazole side chain of the histidine nitrogen and the 6th position is the site where oxygen is to be coordinated. The 5th position of iron is being satisfied by the histidine nitrogen and it is the 6th position where oxygen is to be coordinated.
The heme skeleton is a macrocycle that contains iron at the center of its core and has 4 nitrogen macrocycles from the pyrrole ring that are connected by the methylene bridges.
So, this is the structure of heme. Now, let us see the binding site of oxygen in myoglobin, particularly in reference to the heme unit. Here you can see the iron in 2 plus oxidation state at the center. This is the place where oxygen is going to get binded. This is the proximal histidine and this is the distal histidine. We will see in detail what is the role of distal histidine in the binding of oxygen. Here you can see that the distal histidine is actually not ligated to the iron atom, but the proximal histidine is actually clearly ligated to the iron atom or the iron 2 plus. Here in myoglobin, what happens upon oxygen? What happens upon oxygenation? That's what we are going to see here. So, we know that iron exists in +2 oxidation state and in high spin in the myoglobin form, that is the deoxymyoglobin. So, you can see here iron is existing in the +2 oxidation state, high spin. After oxygenation, what will occur? The oxygen is being coordinated to the iron, but what happens to the oxidation state? Fe2 gets converted into Fe3 and it is low spin. So, in myoglobin upon oxygenation the Fe2 plus high spin state is being converted into Fe3 plus low spin state.
Now, let us see the mechanism of oxygen binding to myoglobin in detail. For this, it's important to understand the structure of myoglobin, which we have already seen. We know that
the fifth position is ligated with the histidine group. It is called the proximal histidine, and the ion which is sitting above the porphyrin plane. The Fe2 plus radius is about 0.77 angstrom in myoglobin, and it cannot actually fit exactly into the cavity. So what happens? It is sitting outside the porphyrin cavity, that is almost 0.45 angstrom above. So now let us see what will happen when dioxygen get binded to the ion center. I already mentioned that ion plus 2 in the high spin state get converted into ion 3 plus in the low spin state. Here is the spin transition of the Fe2 plus to the Fe3 plus low spin state from high spin. This is the deoxymyoglobin, that is before the oxygenation. You can see the spin state here. The ion is present, it is containing the lone pair electrons since it is in the high spin state. So what happens upon oxygenation? It gets converted into oxymyoglobin, and ion is getting converted into Fe3 plus, that is the D5 low spin. Here it is D6 high spin. Here T2G and Eg orbitals. In T2G also you have 2 unpaired electrons, and Eg orbitals also you have 2 unpaired electrons, and it is having unpaired electrons. After the oxygenation, it is having an unpaired electron but in the low spin state. So dioxygen binds at what position? At the 6th position at the ion center, that we have already discussed, that the oxygen will be binded at the 6th coordination site. Although there are huge protein chains, the dioxygen binding or enzymatic transformations occur only at the ion center. We know that around the myoglobin's heme center there are polypeptide chains, but even though this polypeptide chain is present, the dioxygen binding will occur only at the ion center. It is very important. So, in oxymyoglobin, Fe3 plus is present in the low spin state. It is having the D5 form and it is having 1 unpaired electron and the spin is half. And after oxygenation, oxygen present in O2 minus form, that is the superoxide form. The superoxide form is also having 1 electron, 1 unpaired electron. So, it is also having a spin of half.
Here you can see the molecular electronic configuration of superoxide ion. It has 1 unpaired electron.
So, what happens here? The superoxide oxygen radical is having a spin of half, and the oxymyoglobin Fe3 plus in the low spin state is also having an unpaired electron. So, what happens is a strong antiferromagnetic coupling between these two species. So, what will happen? It will become strongly diamagnetic due to this antiferromagnetic coupling between the two unpaired electrons at the ground state. So, at low temperature, we can say that the oxymyoglobin is actually diamagnetic due to the antiferromagnetic coupling between the superoxide radical and the iron 3 plus low spin state. However, at higher temperature, there will be magnetic coupling. So, what happens here is that at low temperature, oxymyoglobin is diamagnetic due to the strong antiferromagnetic coupling, but the oxymyoglobin will get converted into paramagnetic because of the reduced antiferromagnetic coupling between the unpaired electrons at a very high temperature. and this is the oxymyoglobin. It is having an unpaired electron, and when the superoxide radical is also having unpaired electron, and it is getting antiferromagnetically coupled, and this is predominant at the ground state at low temperature. However, the situation is quite different at higher temperature because the antiferromagnetic coupling intensity will reduce at high temperature. The evidence was obtained from
The resonance Raman spectroscopy.
Raman spectroscopy showed that the oxygen-oxygen stretch of oxymyoglobin was found at 1105 centimeter inverse, which depicted that oxygen is present in the O2, that is the superoxide form. Now, we are going to see the role of distal histidine in the oxygenation process. We have already understood what is distal histidine and proximal histidine. Proximal histidine is actually ligated to the Fe2+, while the distal histidine is present in the proximity, but it is not actually ligated to the Fe2+. So, the histidine at the top of the ion center, clearly visible in the protein structure,
Which is not bound to iron.
is just above the dioxygen after the oxygen get binded to the Fe2+. So, this is the distal histidine. It is still present above the binded dioxygen. So, upon oxygen binding, what happens? The dioxygen is getting hydrogen bonded with the distal histidine. So, upon oxygenation, it is getting hydrogen bonded with the distal histidine, which is present in the top of the heme. So, what is happening? It is actually the hydrogen bonding that is occurring between the dioxygen and the distal histidine, and not between the distal histidine and the Fe2+. So, with oxygen, this distal histidine will form a hydrogen bond after the oxygenation. Now, let us see what happens. Dioxygen, since it forms the hydrogen bonding between the histidine NH proton, and it will give further stabilize, or it will further stabilize the Fe3O2 minus conformation. So, that is the role of distal histidine. Since the distal histidine
Forms the NH oxygen hydrogen.
bonding with the oxygen, what will happen? This stabilizes the Fe3 plus O2 minus, that is the superoxide conformation in the angular fashion, and nicely stabilized the NHO bonding. This bonding of hydrogen bonding is actually in the angular fashion, and it will stabilize the histidine oxygen bonding. Now, let us see what happens when carbon monoxide will like to come and bind instead of oxygen. So, we have a competition between oxygen,
And carbon monoxide.
then what will happen? We know that dioxygen will always bind in the angular fashion with histidine and the heme center. Okay, it is forming a hydrogen bonding in the angular fashion. The distal histidine, because of the steric clash force between the carbon monoxide, when we compare, it is having a steric clash with the distal histidine, the carbon monoxide molecule, when it approaches. So, it is not capable of binding in a linear fashion. We know that carbon monoxide is a linear molecule, and it is not capable of binding in a linear fashion due to the presence of distal histidine above. That means the distal histidine is actually blocking the direct linkage of the carbon monoxide molecule, since it cannot bind in the linear fashion. So, what happens? The oxygen is binding, the dioxygen molecule is actually binding in the angular fashion. It can comfortably bind in the angular fashion, and the distal histidine will actually stabilize it. And the carbon monoxide cannot get entered into the, or it cannot bond with the heme center. due to the steric effect. So, we can say that the distal histidine will act as a gate and discriminate the oxygen and carbon monoxide. It makes the 6th coordination site of deoxyhemoglobin accessible to only small molecules, and it also shuttles protons away from the oxygen binding site. So, you can see the picture depicting the carbon monoxide versus oxygen binding here. We know that carbon monoxide is a linear molecule and it prefers this sort of binding, but this is not easy to occur due to the steric repulsion due to the presence of distal histidine. So, what happens? It will have to bend, but this is not possible due to the steric effect between the distal histidine and carbon monoxide. But here oxygen can clearly bind or form the hydrogen bond in an angular fashion, and the distal histidine will stabilize it. So, if we say that the binding affinity of free heme group is actually very high for carbon monoxide, that is free heme group will bind very tightly and easily with carbon monoxide, but the presence of distal histidine in myoglobin will aid the oxygenation further because of the steric hindrance provided by the distal histidine, it will block the linkage of carbon monoxide. So, we can say that the carbon monoxide concentration would increase if there is no distal histidine that will weaken the binding. So, we can simply say that the concentration of carbon monoxide will increase only if there was no distal histidine. Since there is the presence of distal histidine, it will block the formation or binding of carbon monoxide at the heme center. Here we can see that the angularly coordinated oxygen fits very comfortably around the distal histidine, and the perpendicular and linear carbon monoxide moiety cannot. And this distal histidine act as a gate and discriminate between oxygen and carbon monoxide. Now, let us see the mechanism of oxygen binding in myoglobin. We know that myoglobin has a very high affinity to molecular oxygen. It is actually 50% saturated with oxygen at a partial pressure of about 1 or 2 torr, and it is 95% saturated at a partial pressure of 20 torr. So, we can say that the myoglobin is having very high affinity to molecular oxygen. So, the high affinity of myoglobin towards oxygen permit it to store more oxygen efficiently in the resting muscles.
At relatively low pressures, the partial pressure of oxygen in resting muscles is around 40 torr.
And when exercising, when the partial pressure of oxygen
is low, that is around 20 torr also, it is able to store oxygen.
However, when it comes to vigorous exercise, myoglobin releases a significant portion of the stored oxygen as the partial pressure of oxygen drops considerably, very less quantity, that is almost 5 torr. So, at this situation, the myoglobin is forced to release sufficient amount of oxygen, and it will get reduced in the content of oxygen in the muscles. So, today in this lecture we have learned about myoglobin. We have seen the structure of myoglobin, the function of myoglobin. We have also studied how the oxygenation in myoglobin occurs, and we have seen how the distal histidine plays an important role in dioxygen binding and stabilize the oxygenation of myoglobin. Thank you.